All right, we were talking about polar coordinates the last time, and let's remember that if I have my xy coordinate system, and I have a point here, call this point P, with Cartesian coordinates or rectangular coordinates. So these are the rectangular coordinates x comma y. Then we know that a polar coordinate representation of the point P is given by the following pair, r comma theta, where, so this is a polar, these are polar coordinates of P, where r happens to be the distance between the point P and the origin of our coordinate system, and theta happens to be the angle between the x-axis and the radial line that connects the point P to the origin, measured in the counterclockwise direction, and theta is being measured in radians. Okay, now we saw the last time that there are infinitely many polar coordinate representations of the point P, r comma theta being one of them, but we know that r comma theta plus any multiple of 2 pi, this is also a polar coordinate representation of the point P. So these are polar coordinates of P, where k, in this case, is any integer. So it can be negative. Okay. Not only that, but we also found that r can take on negative values. And so another set of polar coordinates for the point P is given by minus r, comma, theta plus pi. All right, so this is another polar coordinate representation of P. And to that, I can add any multiple of 2 pi, any integer multiple of 2 pi. So these are all polar coordinates of the point P. So what do we have here? We have polar coordinates of the form minus r comma theta plus pi plus an integer multiple of 2 pi. These are polar coordinates of the point P, as well as r comma theta plus 2 pi k. And here r is, of course, being assumed to be greater than 0. The interesting thing here also to note is that the origin has the polar coordinates 0, because the distance between the point P, if the point P is located at the origin, then the distance between the 2 points, the origin and the point P, that of course is 0. And then the angle can be anything. So theta is any angle. Okay. All right. Now let's suppose that I have a line. Let's make it this line here. So this is y is equal to x, right? Here's my x-axis and here's my y-axis. And you know what I would like to do is I would like to write this equation in terms of polar coordinates. So what we want to do, we want to express the equation of this diagonal line, x equal y, in terms of polar coordinates. Okay. Well, again, remember from our lesson 1 that we found that there are transformations which take us between polar coordinates and rectangular coordinates. And what we can say is this, that if I have a point, in the plane P with Cartesian coordinates x comma y and polar coordinates r comma theta, then the relation between the Cartesian coordinates and the polar coordinates are given by the following transformations. So these are transformations between polar coordinates and rectangular coordinates. And they're given by the following. X is equal to r times the cosine of theta, and y is equal to r times the sine of theta. Okay. So, of course, one way of converting this equation in terms of rectangular coordinates to an equation involving polar coordinates is to do the following. I can use these transformation equations over here, and I can say, okay, well, x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. So I get r times the sine of theta is equal to r times the cosine of theta. And if I'm assuming that r is not equal to 0, this implies that the sine of theta is equal to the cosine of theta. And what do we know about this basic trig equation? Well, that implies that theta is equal to pi over 4, or any multiple of 2 pi, any integer multiple of 2 pi plus pi over 4. Okay? So an equation in polar coordinates, which is equivalent to the equation y is equal to x in rectangular coordinates, is simply that theta is equal to pi over 4. Here it's understood that r can be any number whatsoever. So, and we can see this. We can see this geometrically. If I look at our drawing up here of the line that's represented by the equation y is equal to x, I see that this angle in here is equal to pi over 4. And so any point on this line can be written in terms of polar coordinates where the angle happens to be pi over 4. Let's take this point down here, for instance. We'll say this is the point. This looks like, let's call this distance from here to here. We'll call that 1.5. So this point here has the polar representation minus 1.5 comma pi over 4. Right? Let's do another. Let's take another example. Let's look at the following. Let's look at this line. here, we'll say this is x equal 2, x-axis, y-axis. And I want to find, so this is the equation of this vertical line in terms of rectangular coordinates. And what I want to do is I want to represent this line as an equation in terms of polar coordinates. Well, one way of doing that is as follows. I can take a point on this line. Take a point on this line. I'm going to draw a line that connects the point to the origin. The distance between this point and the origin I'm going to call r. Okay. I know since this point, let's call this point P, since the point P is on the line x equal 2, I know that this horizontal distance here is 2 units, right? So what can I say about theta in here? Well, I have what I've drawn here is a right triangle. So this is a right triangle. So I know that the cosine of theta is equal to, well, it's the adjacent side, which is 2. I'm dealing with a right triangle. So the cosine of theta is going to be 2 divided by the length of the hypotenuse, which is r. And I can rewrite this equation as r is equal to 2 divided by the cosine of theta, which is equal to 2 times the secant of theta. So in polar coordinates, the equation for the line x equal 2 is given by r is equal to 2 times the secant of theta. Interesting. Here's something that's kind of interesting. This equation, which describes this vertical line, is a very simple equation in terms of rectangular coordinates. However, if I look at this equation over here for this vertical line in polar coordinates, it's a lot more complicated. Okay? So sometimes it's better to represent an equation in terms of rectangular coordinates, and other times it's better to represent the same equation in terms of polar coordinates. Here's another example, an easy one. If I have the circle, just the unit circle, then we know the equation of this unit circle in rectangular coordinates is given by x squared plus y squared is equal to 1. Okay. Well, we learned how to deal with this equation in pre-calculus and in college algebra. Nevertheless, it's kind of a complicated equation. Both the variables appear as terms which are being squared. Now, what is the equation of the same circle in terms of polar coordinates? Well, every point on this circle is a distance 1 from the origin. So that means that r is equal to 1. And theta can be anything. So the equation of this circle equation of the unit circle in polar coordinates is simply r is equal to 1. So you see, here we have the reverse setup. The equation for the circle in polar coordinates is very simple, r equal 1. However, the equation of the circle in rectangular coordinates is more complex. It's x squared plus y squared is equal to 1. So in some situations, it's going to be preferable to work with polar coordinates, and in other situations, it's going to be preferable to work with rectangular coordinates. And this is kind of one of those things that you have to decide depending on the problem that you're dealing with. All right. Suppose I have an equation like this. R is equal to 1 divided by 1 plus the sine of theta. Okay? So this is an equation in polar coordinates. I vary theta. R depends on theta, and so as I vary theta, the values of R change. All right? What I'd like to do is I would like to write this equation in terms of rectangular coordinates. So express this equation in terms of rectangular coordinates. Okay, well, to do this again, what I think I'm going to do is I'm going to appeal to our transformation laws. So our transformation laws, or transformation equations, are x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. Now you really have to master these transformation equations. They're very important, and you will see these later in the calculus sequence, if you're taking the engineering calculus sequence. So not only do you have to have these memorized, but you really have to understand where they come from, and that's not so hard, because remember again, if I have a point P here and x comma y are the rectangular coordinates of the point P, then if I draw this right triangle, label this angle theta, being positive as measured in the counterclockwise direction, and this distance from here to here is r, then I can immediately see from this right triangle that the cosine of theta is equal to x divided by r, and the sine of theta is equal to y divided by r, and these are equivalent to the equations x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. And so it's immediate, almost immediate, how these equations over here can be derived. So even if you forget the equations, you can always draw this right triangle and derive them. All right, well, back to our equation at hand, which is r is equal to 1 over 1 plus the sine of theta. I want to use our transformation equations in order to convert this equation in polar coordinates to an equivalent equation in terms of rectangular coordinates. What I'm going to do, I'm going to multiply both sides by 1 plus the sine of theta. So I have r times 1 plus the sine of theta is equal to 1. And this tells me the following. I have r plus r times the sine of theta is equal to 1. Okay. Now, r times the sine of theta. Well, r times the sine of theta is just equal to y. So I can rewrite this as r plus y is equal to 1, which means that r is equal to 1 minus y. All right? And now I can square both sides of the equation, because here's what I know. I know, look, I have x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. If I square both sides of these two equations, I get x squared is equal to r squared times the cosine of theta squared, and y squared is equal to r squared times the sine squared of theta. If I add these two together, I get x squared plus y squared is equal to r squared times the cosine of theta plus r squared times the sine squared of theta. And this is equal to r squared times the cosine, oops, this should be squared there, cosine squared of theta plus the sine squared of theta. And this is just r squared. So from these transformation equations, I find that r squared is equal to x squared plus y squared. Right? So I want to use that over here. But I just have an r sitting here. And what I really need is an r squared. So I'm going to square both sides of this equation. And now I'm going to write, I'm going to replace my r squared with x squared plus y squared. And there we have it. So here's the rectangular equation that's equivalent to this equation in terms of polar coordinates. Okay. Yeah, well, we could do another one of these. We could do something like this. Let's look at, let's say r is equal to 6 times the cosine of theta. All right. And what I want to do, again, I want to go from an equation in polar coordinates to an equation in terms of rectangular coordinates. Right? So, and again, I want to appeal to these transformation equations. Let's see what we can do. Here I have cosine theta, and over here I have cosine theta times r is equal to x. So it would be nice to have an r here. So I'm gonna multiply both sides of this equation by r. Now sitting here, I have x. So I have r squared is equal to 6 times x. And we know that r squared is equal to x squared plus y squared. That follows from what we did up here. So I have that x squared plus y squared is equal to 6x. Okay. Okay, so think about that a little bit. You might have some questions on it. Here's something. And this is pretty important because this too comes up in calculus. And it's the following. Let me see if I can draw a semi-decent circle. Not so good, but okay. So here I have a circle, and its center is here at the point 1, 0. Okay? So it's a unit circle. The radius is 1, but it's offset. It's not centered at the origin. And what I want to do is I want to find the equation of this circle in polar coordinates. Okay. All right, this takes a little bit of geometry to do. Okay, so I'm going to take a point, an arbitrary point P, on my circle, the circle that I'm interested in. I'm going to connect P to the origin. I'm going to say, okay, since we're dealing with polar coordinates, the distance between P and the origin, I'm calling that R. So this distance from here to here, that's R. right? And then what I'm going to do, I'm going to come down here to this point, and I'm going to connect P to this point down here. Now, here's where something that you studied years ago comes into play, and that's a little bit of the geometry. You'll remember from geometry that if you have an inscribed triangle whose hypotenuse or whose longest side happens to be a diameter, then this angle here happens to be a right angle. So this angle in here is pi over 2. So now I'm dealing with a right triangle. So I have this triangle here, happens to be a right triangle. And I'm interested in this angle here, theta. What can I say about theta? So I have a right triangle. I have an angle, which is not the right angle of that triangle, that right triangle. And I'm kind of interested in, hey, what is the cosine of theta? Well, you'll remember the cosine of theta is equal to the adjacent side, which is r, which has length r. So it's the length of the adjacent side. I'll do that. So it's the length of the adjacent side, that's the side adjacent to theta, divided by the hypotenuse. And the hypotenuse is the side opposite the right angle. So that's this side here. And what is the length of that side? Well, the distance from here to here is 1. So the length of this side is 2 units. Yellow is not a good color because it is hard to see. All right, so I'll put the 2 there. So the length of my hypotenuse happens to be 2 because it coincides with the diameter of the circle. So what I find is the following. I find that the equation for this circle is just 2 times the cosine of theta is equal to r. All right, which sometimes is written as 2 is equal to r times the secant of theta. Right? So that's pretty important. Okay, let's conclude our lesson here, and we'll continue with a look at the next section in the book, 8.2. Okay.